Okay, cool. So you'd be wise just to do this part with me, but as has often been the case with these, there's 3 tabs down on the bottom. And the first one is really just me teaching you or showing you the commands that exist in Excel to do the same things that you already know how to do. And this is a pretty good one because we're going to do it quickly in the calculator as we, I want to say we already know how to do, but it's like we're getting better at. But then we're going to do the same thing with Excel. And so this isn't really part of the assignment, but it does help for you to type the commands and recognize what they are and kind of get a sense of how it works. And then you'll be good for the 2 problems that I'll introduce in a little bit. So anyway, this first situation is a recent study found the average age of cars on the road in 2013 is normally distributed. Notice it says it's normally distributed. That's one of the requirements actually to do the things we've been doing in chapter 8. Is the original data, the parent data, is it normally distributed? And that kind of makes sense, doesn't it? Cars on the road, you'd have a few really old ones, like 40 years old. You'd have a few brand new ones, but there'd be lots of them that were like 5 years old. And so that could be true. And so the average age was 8.3 years for the cars, and the standard deviation was 2.4. And so the question is, find the percent of cars you would predict to be more than 10 years old. So I drew a graph of it over here. So we're talking about this area to the right, bigger than 10. And so as you know, and I would recommend you do this with me, just for practice, because this is kind of what the test is going to feel like. So if I say using the TI-84, and of course the normal CDF function, since it was normally distributed, we can say normal CDF. And lower limit, that'd be 10. Upper limit would be whatever, 900 or something. And then list the mean and the standard deviation, and we would know what percent of cars. We'd be able to predict again. That's what's so cool about this. We can actually predict, just knowing the mean and the standard deviation, we can predict how many cars on the road are that old. So I'm going on the calculator, second distribution, normal cumulative distribution function, cumulative meaning add all of these up. My lower limit is 10, my upper limit, I'm going to say 900. My mean was 8.3 and my standard deviation was 2.4, if I remember right. Yep. And so my calculator says that is 0.239. I'm rounding randomly. And so, that's the kind of thing I'd want you to be able to do on the test. So, oh, that's kind of cool. That's interesting. So if the mean is really 8.3 and the standard deviation is 2.4, I could predict that a quarter of the cars, 24%, a quarter of the cars on the road are over 10 years old. That's interesting. Of course, in terms of pollution or traffic, or I'm a car dealer, maybe that's kind of good for me to know. I can see somebody wanting to know that. But the question is, can we get Excel to produce the same answer? That's what we're really after today. So I say here, and this is actually meant to be self-explanatory. I just want to talk and give you a little time to think about it. But we used back here the normal CDF function. What command are we using now? I'm going to highlight it a different color. We're using norm dist. And so that's Excel's version of normal CDF, norm dist. Again, don't see this as something that you would memorize, because I can't, if you see me on the street 2 weeks from now, I wouldn't remember what the command is in Excel either. And I've taught this class a bunch of times. So
Doug, are we supposed to be seeing your screen?
You are, and you're not. So thank you for speaking up.
Sure.
Because I can fix that. You are supposed to be seeing my screen. Are you now seeing it?
Yes.
Okay, good, just in time. So let's use the norm dist. And again, this is nice, as I said, self-explanatory, because I even showed you the command. And so okay, what's the command? You may be familiar, you should be familiar with the fact that in Excel, you have to put an equal sign in front of it if you want it to do something. So I told you the syntax right here. So the syntax is, oh, isn't that weird? It's in a different order. And also take a look at this. Notice the norm dist command is actually, in a sense, not as good. Remember how up here we could type in the upper and the lower limit? Whereas norm dist, it says you put in the value we were interested in is 10 years old, but we wanted the area above that. Well, notice in red here, I said, unfortunately, it returns the area to the left. Do you agree that's not what we wanted? We wanted the area to the right. And what's cool about the calculator is we can just say lower and upper limit and make it tell us whatever area we want. And unfortunately, norm dist is a little limited in the sense that it only tells you the area to the left of 10. So how are we going to get that to work? I mean, it's only going to, if I put 10 in, it's going to tell me this area over here. There's no way around it. So I can't say from the left of 90 because it's going to go all the way across here. Does that make sense? Who can tell us based on algebra, if I get this area over here, how could I know the area that I want? I mean, let's say the area over here was 0.8. What's the area here? 1 minus that, right? Because the area under the curve is 100%. So unfortunately, the norm dist command will only tell me this area over here, which is a bummer because in this case, that's not what I wanted to know. But since the area under the entire curve is 1, couldn't I just go 1 minus this area and then I'd have the area I wanted? So it's like in a little bit of an extra step. So, okay, fine. So equals, watch this, do this with me, equals norm. And notice when you start typing, it starts popping up the options. I'm going to type the whole thing. Notice there's some other commands here like norm.s.dist, norm dist. I mean, there's all kinds of commands in here. The one that we're using is norm dist. Notice there's one called norms dist with an S in it. And so this is an important concept, at least you can see, but notice there's like 8 of them in here. So man, that's kind of confusing. But we're doing norm dist and very possibly norm.dist would also work. I just don't remember off the top of my head. My gut memory is some of these commands were like in older versions and some were in newer versions. But anyway, whatever. Oh, you have to do the dot. So yeah, the one that I was proposing is just the one that says, and I'll probably play with this. I'll show you. We'll just experiment together. But I was saying the norm dist command. And so, and then notice the syntax. The syntax is in a totally different order. First, you put X, which is our 10. And remember, automatically, it's going to give us the area to the left of 10. So we don't get to put in 10 and 900. We just have to say 10, and it's going to produce the area to the left. And then I put in the mean, which we said was 8.3. So I got to have the syntax in front of me. Does that make sense? Also, though, although I have it written here in the green box, do you see that right down here at the bottom, it's actually telling you the syntax as well? So it's not like you have to have this memorized. And so right now, mean is highlighted because I'm there, but as soon as I put a comma, it jumps to standard deviation. So I put 2.4. And then as I said up here, but didn't comment on, what about this last one? You put true because it's basically, it's true or false is what you have to put here. And I think that has to do with, are you adding them up or not? Notice it says true is the cumulative distribution function. Isn't that what the calculator was, norm CDF? So true means, yeah, I want to add all of those up. So you just type the word true. Now, notice that gave us the area to the left. So that's not the answer we're after. But how do you fix it? Well, as Shelly said, all I have to do is go in here to the equal sign and say, oh, actually, I want 1 minus that answer. And notice now they agree. I get the same answer with Excel that I got with the calculator. So I'm expecting when you do the next 2 tabs that you probably have to look back at that, right? You know, like you didn't memorize that. You got to look back at this. You should have some sort of clear notes. So the syntax of how that command works. Now, quickly, I'm curious. Remember how there was another command that was norm.dist? If I go in here and put dot in there, will I still get the same answer? Notice I do. So, you know, I don't want to look into why, who cares, but it looks like norm dist or norm.dist. I don't know which one is one better. I don't know. They seem to both be working, so who cares? Cool. So this is one type of problem we had where you know the boundaries that you have. You know that, hey, I'm interested in cars where the boundary is 10. And then I'm interested in above that. But then there were problems where we went the other direction, which was I knew the percent, but I wanted the boundary. So notice same exact data, except for this time the person has a different question. Their question is, find the age that defines the top 2% of oldest cars. And again, I hope you see that as at least a somewhat interesting question. But you know, how old are the top two, based on this mean and standard deviation, how old are the top 2% of cars? Are they over 14 years old? Are they over 18 years old? I mean, that's kind of an interesting question. So y'all should already know how to do this on your calculator. So again, let's do this together. To find the answer on the T84, I'm just reminding you, we use the inverse norm command. And we said inverse norm, and just like we saw a second ago, we were stuck with area to the left, right? With your calculator. Unfortunately, you couldn't say area to the right of 2% unless you have one of the most modern calculators, the TI-84 plus CE. So you would say, oh, well, I was interested in the top 2%, but I can't do that. I can only enter area to the left. And so if this is 2%, 1 minus that is 98%. So I have to put 0.98 in for the area to the left, and then the mean and the standard deviation. So inverse, again, I would recommend you do this with me. Inverse normal area to the left is 0.98, mean was 8.3, standard deviation was 2.4, and I got 13.2. Did you get that as well? This is the kind of question that will be on your test for sure. Again, that's interesting to know. Oh, if your car is older than 13 years old, let's see, what is today, 2022. What does that take us back to? 9? Gosh. So if your car is older than 2009, then you, according to this data anyway, your car is in the top 2% of oldest cars rolling around on the road, over 13 years old. Again, that's just interesting. Maybe that's how you justify wasting your money on a new car. But the question again is, in this section is, you know, how do you get Excel to do the same thing? Well, notice it's kind of interesting. The command in your calculator was inverse norm, whereas the command in, and I'm going to highlight it and turn it red, the command in your Excel is actually norm inverse. So part of me says, cool, it's the same thing, but then part of me is mad because it's like kind of like the Excel people didn't talk to the calculator people. From our perspective, it would have been nice if they're the same exact commands, right? But they didn't talk to each other. They didn't care. So inverse norm, norm inverse. So notice this is identical. Isn't that kind of cool? So this tool asks for the probability again on the left. So this is actually a perfect match to what your calculator does. It's also to the left. And notice the syntax. Probability goes first, and then mean and standard deviation. Isn't that exactly the same order? So in a sense here, it does look like they talked to each other, even though they didn't. So I say, fine, equals norm. And notice there's also norm dot inverse. My guess is, as we discovered a second ago, if I type norm inverse or norm dot inverse, they'll probably both work. So area to the left, 0.98. Again, to help you with the syntax of all of this, notice I'm in the first comma right now. So the word probability is highlighted. And again, notice isn't it interesting that in, you know, like in my notes, I said area to the left, whereas they said probability. Do you see area and probability is the same thing? The area under that curve is 1, but it's also the probability, the proportion of people. So because I'm in the first comma, probability is highlighted. As soon as I hit the comma, it jumps to mean, and it's kind of telling you, dude, enter the mean now. Great, 8.3. Comma, jumps to standard deviation, 2.4. Close the parenthesis, bam, get the same exact answer. Notice apparently I must have went in here and told that to round off to 2 decimal places. I can't remember. But remember, you can control that. As a shortcut, these 2 percent signs or decimal points up here are telling you how to do that. You can click this and increase the decimal if you had some ridiculous reason to have it accurate, or if you said I'd like to round it off. That's just a fast way to access that. So apparently I went in there and set it to 2 decimal places, since that seems to be what's happening. So again, the point is I can get Excel to do the same thing the calculator does. The 2 main things we did were finding the area when we knew the location, Or if we knew the area, we could find the location. We just found the location, the line that divides the bottom 98% of cars to the top 2% of oldest cars, and we found the line. It's 13.2 years, or even 13. And then remember some of our calculations just recently for when we were hunting for the error, which is what you'll be doing on the next page. When you're hunting for the error, we actually needed a z-score. Remember, z of alpha over 2. So how did that work? Well, that was also norm inverse. It's just that your mean was 0. We put the mean in as 0 and the standard deviation, highlighting those. The standard deviation is 1. Isn't that what we did in our calculator? This is identical. Nothing has changed here. So that's kind of cool. So as a part of finding your error for, in this case, a 94% confidence interval, remember that's the middle 94%, which would leave an error of 6%. Split in the two tails would be 3%. So I'll just use this picture up here as an example. But if this was 3%, then wouldn't the area to the left of that be 97? So in order to get this correct z-score, then I'd have to say equals norm dist, spelled correctly. Probability would be 0.97. And the mean is 0 and the standard deviation is 1. So it didn't like that. Anybody can see why? I can't see what it didn't like. Yeah, because I did norm dist, not norm inverse. And so, I just got excited, wasn't paying attention. Now, what do you think the note says behind? How many things did norm dist need to know? 1, 2, 3, 4. So when I said norm dist and only told it 3 things, it said error because it didn't know what to do. In a sense, I got lucky because I wasn't really thinking correctly. And if it had given an answer, I probably would have thought, oh, there's the answer. So let's see, what does it say? It says you entered too few arguments. That kind of makes sense, right? So norm dist and norm inverse. If I enter norm inverse, it's asking for 3 arguments, and now it says, oh, your z-score then is 1.88. So you can get all this stuff straight from Excel. Now, let me just introduce these next two problems. Notice there's a 9.1 question and a 9.2 question. We're looking at all of chapter 9 at the same time. Notice at the top here, the question of interest. What is this person curious about? Notice you have all these breaking strengths. And by the way, this is how concrete is really tested. I think maybe I've told you this before, but they actually fill a cylinder that's 12 inches tall and 6 inches diameter when they're pouring like a bridge, where if the concrete fails, people die. It doesn't so much matter if your driveway fails, right? I mean, maybe you're mad, but no one dies. But when you're pouring a bridge, they actually have to take some of the concrete from every single truck, pour it in these little cylinders, let it harden for 28 days, because that's how long it takes concrete to get to its full strength. And then they push this hydraulic ram down on it and see how much force it can withstand. And if it withstands it, remember the concrete that's in the bridge has also been sitting there for 28 days. But if this fails that test, then they got to go jackhammer all that concrete out because someone screwed up. Someone screwed up the process a little bit. But can you appreciate, it's a good thing they do that? How many bridges have you driven over without thinking about it at all? But it's like somebody had to do a lot of work to make sure that didn't get screwed up. Well, can you appreciate that if you break this concrete, they're not all going to break at the same strength? There's going to be variation. So notice when they broke it, the first one broke at 1,182 pounds per square inch, the second one at 1,122, the next one at 1,373, and so forth. Notice this one was really low, 918. That was like the weakest one. Well, there's a 913. So you got a lot of variation, right? I mean, is that what we've been studying in this class? And so my question to you is, great, you took a sample of all these different breaking strengths. How many are there? Looks like lots, 60 some. So then I just ask you a bunch of questions. This is an example of, in a sense, what somebody would want to be able to do. This is also something that you're, in a sense, going to be doing for your final project. So sample size, and notice the question here, the number breaking over 1,200, and then here's the question at hand. Because the question of interest was a percent, what was this person curious about? They wanted to know what percent of all of these test cylinders break at over 1,200. Notice even though the data look like it would be a mean. The question this person was curious about are what percent of them break over 1200. And so their question of interest was a percent. Their parameter of interest in the language of your assignment was a percent. So they're curious about a percent. So then you get that percent, and then you realize, well, that's just one sample. And so if I did another sample, I wouldn't get the same answer. I realized this is a p-hat. It's a sample proportion. I get the standard deviation, and then the most important part of this probably is, can you create the confidence interval for that? Notice I'm asking you to give the lower limit and the upper limit. And so you recognize that p-hat, which is a sample proportion, is not the same as the population. So can you explain the meaning of that and answer a couple of questions? Now, this is very important, what I said there in red. I don't want to see numbers in these cells, because then I'm just going to think you did it with your calculator, because you're more comfortable with your calculator, right? But remember, you're not going to use your calculator in the real world. So in a sense, I'm forcing you to learn Excel. You're more than welcome to check it with your calculator, just so you're thinking. But when I click on these, like sample size, I shouldn't see a formula, or number breaking over 1200. You can just count them over here. But I should see formulas. I should see formulas for this stuff. I should see an Excel formula right here to find that lower level. Same data. Well, not quite the same data. I'm on 9.2 now. Here, what's the person's question? Maybe this is the more natural question. This person was just curious about the sample mean. What's the average breaking strength? They didn't want to know what percent are stronger than 1200. They wanted to know what's the mean, what's the average breaking strength of this sample of concrete. I don't think this is the same number. This is not the same test. It's a totally different test. But this person was curious about the sample mean. So could you create an 80% confidence interval, realizing that, again, this is a sample mean. It's not the population mean. But in the real world, people want to know what the population mean. Also, notice a hint right here. When the data was a sample mean, did we use a z-score? No, we used a t-score, right, in your notes. Notice I'm telling you right here the command for that. So we didn't practice that. We had a norm inverse command a second ago, or inverse norm. I've already forgot which one it was. But here I'm telling you, you need t dot inverse here to get your t-score. Again, as I always say, you should get 100% on this. Not because I explain it for 5 minutes and then you're just awesome, but because you should ask me, is this right? Am I doing this right? Check this with me, like ask questions. The point is to learn from this, not just to get some assignment done. Go ahead, Garrett.
I got your link, but where can I find some files?
It is in MyOpenMath and in the Excel labs, the green tab, lab number 5, the bottom one.
Okay, thanks.
Yep. So I'm asking you questions that I think are extremely practical. This assignment is test prep. It's also like what you should leave this class knowing, what would actually be marketable skill if you left this class being able to do. And I'm having you do it in a context that would be in business or something like that. It'd be way better to do it here than with your calculator, perhaps. And so this should feed into your final project. It should help you with the test. Like, take this really slowly and think about it. We have 40 minutes now, and I'll probably give you a little bit of time at the start of the day tomorrow, maybe 20 minutes or so, for me to also walk around, because I really would like to interact with you one-on-one and kind of check your answers relative to mine and teach you something. Because the point of, as I said, the reason I want you to get 100%, well, I want you to get a good grade in this class, but more than that, if you get something wrong, I want to have a conversation with you so you get smarter, so you actually know something, which again, will help you on your test. So when you either ideally attach this in MyOpenMath and send it to me, let's see, in my syllabus, I say this is due the 7th. So you have 6 days or something. You have a long time to do this. Plenty of time to kind of check with me after class, those kinds of things. I'm just going to click on these two, and I'm not just going to look at these numbers. I'm going to click in here and see, is there a formula in here? If there's just a number, as I said down here, I don't want you to do the work on your calculator and just enter the numbers in Excel. Your cells should have Excel formulas behind them. If I click on this and I don't see a formula up here that's in Excel, you're not going to get as many points. I want you to understand how to do this in Excel. I'm very aware that is more of a pain. Check it with your calculator if you want to, because you are going to take a test, but do this in Excel. Also, you're more than welcome to have junk off to the side, and I'll shut up after this. But like for a confidence interval, don't you need an error? And the error was like a t-score multiplied by the standard deviation. If over to the side here, you want to have like a formula for your t-score and a formula for your standard deviation, and you want to have, you know, a little calculation here and a calculation there, like an equal sign, and then over here you finish it, like that's fine. You don't have to have it all just sitting in one cell. But I just want to see that you did it in Excel. All right. So start wading into this. You guys on Zoom, speak up and I'll come back, but I'm just going to wander around.